Hello everyone, David Ostrowski here, MCS 2534, Data Structures and Algorithm Analysis. In this recording, we're going to be talking about priority queues and heaps. Let's take a look at the overview of the priority queue ADT. So a priority queue stores a collection of items. An item is a pair, has a key and an element. The main methods involved include insert item with key of K, element of O, remove an item here with the smallest key. Additional methods include min key, which returns but does not remove the smallest key of an item. Min element, which returns but does not remove the element of an item with the smallest key. And size, okay, or as well as is empty. Some popular applications of priority queues can include standby flyers or auctions. Comparator ADT, this would encapsulate the action of comparing two objects according to a given total order relation. A generic priority queue uses a comparator as a template argument to define the comparison function, which could include less than, equal to, or greater than. The comparator is external to the keys being compared, thus the same objects can be sorted different ways by using different comparators. When the priority queue needs to compare two keys, it uses its comparator. Okay. We're going to use comparators in C++. The comparator class overloads the parentheses operator with a comparison function. Here, in this example, they can compare 2 points in the plane lexicographically using the following code. Total order relation here, the keys are in a priority queue. They could be arbitrary objects on which an order is defined. Two distinct items in a priority queue here can have the same key. And here it employs the mathematical concept of the total order relation less than or equal to. And this is broken down into reflexive property, anti-symmetric property, and transitive property. When sorting with the priority queue, we can use a priority queue to sort a set of comparable elements. Here, you insert the elements one by one with a series of insert item E, E operations, and remove the elements in a sorted order with a series of remove min operations. Here, the running time would depend on the PQ implementation. On the right is an algorithm for a priority queue sort. You would input a sequence S, a comparator C for the elements of S. The output sequences C sorted in increasing order according to C. And here you would initialize P to the priority queue with comparator C and have the following while condition while S is empty. You would perform the remove with S first and do an insert item of E, and while P is, or while S is not equal, is not empty, essentially, right? You insert the items, and while P is empty, then you have the min element and remove the minimum and insert the last. It's identified. List-based priority queue. An unsorted list implementation. Here you would store the items in a priority queue in a list-based sequence in arbitrary order. The performance would be big O1 of insert items, since you can insert the item at the beginning or end of the sequence. Here, remove min key, and min element take big O(n) time, since you have to traverse the entire sequence to find the smallest key. For sorted list implementation, you can store the items of the priority queue in a sequence, sorted by the key. Here, the performance of insert item would be big O of n. Here, you have to find the place where to insert the item. Remove min key, min element here would take big O one time, since the smallest key is at the beginning of the sequence. Selection sort is a variation of the priority queue sort, where the priority queue is implemented in an unsorted sequence. The running time of the selection sort, here you'd insert the elements into the priority queue with the n insert item operations, taking big O of n and removing the elements in sorted order from the priority queue with n remove min operations, taking the time proportional to 1 incremented up to n. Here the selection sort would run in big O of n squared. Here they have an exercise. We're going to fast forward through that. Insertion sort. Here, this is a variation of the priority queue sort, where the priority queue is implemented with a sorted sequence. Here, the running time of insertion sort would include inserting elements into the priority queue with n insert item operations, taking time proportional to 1 incrementing till n, and removing the elements in sorted order from priority queue with a series of n remove min operations, taking big O n time. Here, the insertion sort would run in big O n squared. In place insertion sort, instead of using an external data structure, we can implement selection sort and insertion sort in place with only big O1 extra storage. Here, a proportion of the input of the sequence itself serves as the priority queue. For in-place insertion sort, you would keep sorted the initial portion of the sequence, and you swap elements instead of modifying the sequence. Now looking at heaps and priority queues. So what are we referring to as a heap? The heap is a binary tree for storing keys at its internal nodes and satisfying the following properties. The heap order for every internal node v other than the root is where the key of v would be greater than the key of the parent of v, and a complete binary tree would be where h is the height of the heap, and for I equals 0 up to h minus 1, there are two to the I nodes of depth I. At the depth h minus 1, the internal nodes are to the left of the leaf nodes. Here, the last node of the heap is the rightmost internal node of depth h minus 1. Height of a heap. Here, the theorem is presenting the heap storing n keys, which has a height of O log n. No surprise. Okay. The proof here, you can apply the complete binary tree property. Here, h would be the height of the heap storing n keys. Since there are 2 of I keys at depth I, going from h to all the way to h minus 2, at least 1 key at depth h minus 1, and we have n greater than or equal to 1 plus 2 plus 4 all the way to 2. through 2 to h minus 2 plus 1. Thus, 2 greater than or equal to 2 to the h minus 1, and an example of h less than log of n plus 1. So you have the depth here, the associated keys, and the associated metrics. Heaps and priority queues. Here we can use a heap to implement a priority queue. Here we would store a key element item at each internal node. We would keep track of the position of the last node, and here in the illustration you only show the keys in the associated pictures. Inserting to a heap, you would modify insert item of the priority queue corresponding to the insertion of key K to the heap. Here, the insertion algorithm consists of 3 steps. You find the insertion node Z, the new last node, store K at Z and expand Z into an internal node, and then restore the heap order property. Up heap, after the insertion of a new key K, the heap order property could be violated. Here, an algorithm up heap restores the heap order property by swapping K along with an upward path to the insertion node. Up heap terminates when the key K reaches the root or a node whose parents has a key smaller than or equal to K. Since a heap has a height big O log n, up heap runs in big O log n time. Removal from a heap. Method remove min of the priority queue ADT corresponds to the removal of the root key from the heap. Here, the removal algorithm would consist of 3 steps. You'd replace the root key with the key of the last node W. You'd compress W and children into a heap and restore the heap order property. Down heap, after replacing the root key with the key K of the last node, the heap order property may be violated. Algorithm down heap restores the heap property by swapping key K with the child with the smallest key along with a downward path from the root. Down heap terminates when the key K reaches a leaf or a node whose children have keys greater than or equal to K. Since a heap has a height big O log n, down heap would also run in big O log n time. Updating the last node, the insertion node, can be found by traversing a path of big O log n. This would require going up until left child or the root is reached. If the left child is reached, go to the right child, go down to the left until the leaf is reached. And you would apply some algorithm for updating the last node after a removal. Sort of good stopping point. I'm going to continue on with this material in the next recording. Thanks for listening. Talk to you soon. Any questions, feel free to reach out. Thank you.